Hello, everybody. Welcome back. Thank you for joining me again. And we're going to continue our conversation about probability distributions, but we're going to be working specifically with a binomial probability distribution. And so binomial probability distributions are going to allow us to work with circumstances in which there are two outcomes. When you flip a coin, you can get heads or you can get tails. Does that make sense? When you plant a seed, what are the outcomes that you can have? Well, it could germinate, right? Or not germinate. Whenever we're working with circumstances where there are only two outcomes, we're going to be able to use binomial probability distribution. I did not finish writing this. Another example would be like if a company is checking if, their computers or their printers or their cars, making sure that it's not defective and that it's acceptable. That's also a situation where, there's only two possible outcomes. So acceptable, a car could be acceptable or a computer could be acceptable, or it could be defective. All right. So if we are in a situation where we only have two outcomes, here are three examples that I just gave you, where we can look into using the binomial probability distribution. But another thing is that there are actually conditions in order for us to actually use it. So that's the next part here. Okay. So first is like, okay, is there only two outcomes? Okay. Then next thing is, okay, let's check if all these conditions are satisfied. So the binomial probability distribution results from a procedure that satisfies these four conditions of a binomial experiment. What are these conditions? So like I mentioned, each trial has only two outcomes, right? Like heads and tails, acceptable or defective, germinating, not germinating. There's only two outcomes. It has only two outcomes. Yeah, it sounds weird. Each trial has two outcomes. That was definitely a typo, and I apologize. So each trial has only two outcomes. Okay, the other condition is that there's a fixed number of trials. So for example, when we flip a coin, maybe we say, after flipping 5 coins, what's the probability that we get 3 tails? Okay, but there has to be a stopping point. We have to know like how many times we're going to do this. The other condition is that the trials are independent. And hopefully you remember from chapter 4 that the word independent means that the probability of one thing is not going to affect the probability of the other. Okay. And so here we're going to be continuing using that idea. We want to make sure that when we do a trial, when we plant one seed, the probability of one seed germinating is not affecting the probability that the other germinates. Or when we flip a coin, the probability that I get heads on my first toss is not going to affect the probability that I had heads on the second toss. Make sense? These events need to be independent. The last condition here is that the probability of success remains the same in all trials. When we flip a coin, the probability of getting heads is always going to be the same, 0.5, 0.5, 0.5. In order for us to have a binomial experiment and use a binomial probability distribution, we need to make sure that the probability of success remains the same in every trial. The probability that a seed germinates is always the same. The probability that that a computer is broken, that it's defective or not defective, that probability has to stay the same for every single trial. The central problem of a binomial experiment is to find the probability of X successes in N trials. So you're going to be able to see that often whenever you're looking at practice problems, that they're going to ask you, what's the probability that 3 seeds germinate out of 7? Or what's the probability that I get 2 heads when I toss a coin 5 times? Okay, so that's always a probability of X successes out of N trials. I'm going to go ahead and highlight that just because I want to make sure that you understand that that is what you're going to be looking at, especially in 5.2, is the successes out of a certain number of trials. And again, these trials need to be binomial. Okay, there's only 2 outcomes. I do want to make sure that I know that again, one of the outcomes or events of a trial is going to be called a success, and the other one is going to be called a failure. A success doesn't necessarily mean it's going to be a favorable outcome or a desirable outcome. Okay, it just depends on what you end up choosing to be a success. For example, I want to know how many computers are defective, 5 computers be defective out of 10 computers, right? Maybe my success here is defective because I'm looking for defective computers. So again, a success does not mean favorable or desirable. Right? And a failure doesn't necessarily mean that it's going to be negative or unfavorable. I just want you to understand that, just because it says success doesn't imply that it's a positive thing, and a failure is that it's a negative thing. We're going to describe one outcome as being a success and one outcome as being a failure. If we're interested in defective computers, then a success would be having a defective computer, and a failure would be having an acceptable computer. Let's go ahead and talk a little bit about notation. You guys know I'm all about notation, making sure that we know what n is, what x bar is, what is mu, what is sigma. So we're going to denote capital S as a success. So whenever you see success, we're just going to put an S. We're not going to actually write down the whole word. All right, so S is going to be a success, and F is going to denote a failure. So we're only going to have 2 outcomes. One is going to be a success, and the other one's going to be a failure. We're going to be using little p is going to be the probability of success. If heads is my success in this case, then that would be p would be equal to 0.5. And we're going to use little q to denote the probability of a failure. Okay, so again, for example, we're flipping a coin, then my little p is going to be 0.5. That's the probability of getting heads. And my little q, the probability of failure of not getting heads, well, it actually ends up being the same thing in this case. We can actually find Q by using P. P and Q have to add up to 1. The probability of success plus the probability of failure has to add up to 1. So Q is the same thing as 1 minus P. So if we know P, if we know the probability of success, we can find Q, which is the probability of failure. Okay? Because P, the probability of success, plus the probability of failure has to equal 1. And all we do is subtract P from both sides, and we get this formula here. Okay, just using our algebra, just basic algebra. The other notation is I want to make sure that we understand what little n is. That's our sample size. This is the fixed number of trials, and x, and this is going to be just a specific number of successes in n trials. Okay, let's go ahead and do an example just to make sure that we're understanding all of these ideas. What a binomial probability distribution, what is that? So let's go ahead and do example 1 here. So example 1 says, consider the experiment consisting of 10 tosses of a coin. Determine whether or not it is a binomial experiment. Let's check if the conditions above are satisfied. Remember, there's 4 different conditions. Step 1, how many trials are there? Is it a fixed number of trials? And so, yes, we do have a fixed number of trials. There are a total of 10 trials, which are tosses in this case. And again, we're just tossing the coin. So it is an n, so they are identical. Now it says, are the n trials independent? Yes, they are, right? Because again, the probability that we get heads on the first one is not going to affect the probability that we get heads on the next one. Okay, so they are independent because the former toss will not affect the next toss. And now the next question is, does each trial only have 2 outcomes? What will be denoted as a success and what will be denoted as a failure? Okay, well, let's answer the first question. Every trial, in this case, a trial is a toss. So every time I toss a coin, do I have only 2 outcomes? Yes, I do, right? Heads or tails. So yes, that answers that question. And then I'm going to have to denote one as a success and one as a failure. Here we can say each trial or each toss has 2 outcomes, and then we could decide what we want to be a success and what we want to be a failure. Each trial, which is a toss in this case, has only 2 possible outcomes, a head and a tail. We're just going to let a head be called a success and a tail be called a failure. We want to make sure that there's a fixed number of trials, that the trials are independent, that there's only 2 outcomes in each trial. And the last one is that the probability of success is always the same. In step 4 is asking, what is the probability of failure, Q, and the probability of success, P? We said that a success in this case would be getting heads. The probability of getting heads is 1/2, which is 0.5, and it is always constant. Let's go ahead and write this down. Little p is a success. The probability of success is 1/2, which is the same thing as 0.5. So the probability of success is 0.5. The probability to failure, remember failure in this case, we said that would be a tail, and that's also 1/2. And now we have to check that both of them add up to 1. And they do. 0.5 plus 0.5 is 1. So let me just write down the probability of success is 0.5, and the probability of failure is 0.5. The sum of these two is 1. Okay, and the probability remains the same every single toss. It's always going to be 0.5, 0.5, 0.5. A box contains 20 cell phones, and 2 of them are defective. 3 cell phones are randomly selected from this box and inspected to determine whether each is good or defective. Is this experiment a binomial experiment? Well, we have to go ahead and check those 4 conditions. We have to have a fixed number of trials. We have to have only 2 outcomes for each trial. We need to make sure that the trials are independent. And the last one is that the probability of success or the probability of failure stays the same throughout each of the trials. Step 1 is, how many trials do we have? Do we have a fixed number of trials? There are a fixed number of trials. And in this case, a trial would be inspecting a cell phone to tell whether it's good or if it's defective. So there are a fixed number of trials. So this example consists of 3 identical trials where a trial represents the selection of a cell phone. Okay. Now, the next one that we want to check is we want to make sure that there are only 2 outcomes for each trial. And again, in this trial is selecting a cell phone. So every time we select a cell phone, are there only 2 outcomes? Yes, it could either be good or it could be defective. There are only 2 outcomes when selecting a cell phone. It can be in good condition or it can be defective. All right. Okay, so far it's looking good. Go ahead and look at third one. Is every trial independent? So for example, when I select the cell phone, right, the probability that one is defective, does that affect the probability the next one is defective or the probability that it's not defective? Let me go ahead and draw this out because I think it's going to be helpful to see a visual. So 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18, 19, 20. So think about it as these are our 20 cell phones. We do know they do tell us that 2 of them are defective, right? So maybe this one is the defective one and this is the defective one. Let's suppose that, the success in this case would be defective. Let's look at the probability that a phone is defective, okay? So let's suppose that we get one phone first. What's the probability that if I get the first phone, that phone is defective? Well, that's going to be, there's 2 defective phones out of 20, right? That's the probability of being defective is 2 out of 20, which is 0.10. Now, let's suppose that that phone that I got, the first phone that I got was defective. So now let's suppose that was a defective phone and that's the one that I pulled out. So I already did that one, right? Now, the next one that I get, what's the probability that phone is defective now? Well, now the probability that the phone is defective, because the first one was defective, now the probability is 1 out of 19. But notice that there's something happening here. We now have less defective phones because we took one out. Now we have one less defective phone. That means that my probability that the next one is defective has now lowered. Let's suppose that we have all our phones, right? We have our 20 phones. The probability that we select one at random that it's defective is 2 out of 20. If we remove one that is actually defective, now the probability that the next one is defective, now it's 1 out of 19 because we have one less defective phone. Let's suppose that we end up getting 2 phones that are defective, like we end up getting defective. Now, what's the probability that the third phone is defective? Well, there's no more defective left. And so then the probability would be 0. There's 0 defective out of 18. Notice that the probability of defectiveness is changing. It's not staying the same. The probability that the first one is defective is going to change the probability that the next one is defective. Because if we end up choosing defective first, and then the second one it happens to be defective, then the last one we know is not going to be defective. So notice that the probability of the first ones did affect the probability of the last one here. Okay, because again, if we choose defective first, and then we end up getting defective, right? Then we know that the last one is going to be good. The probability of the previous ones does affect the probability of the last one. So that's what we lose the independence. Remember, independence means the probability of one is not going to affect the probability of the other. Okay, so I'll try to figure out how to write this down for you all. The trials are not independent. The outcome of the first selection affects the outcome of the second selection, and so on. Once one of the conditions is broken, we don't have a binomial experiment anymore. Okay, so it doesn't matter if maybe if 3 out of 4 are satisfied. The moment one breaks, it's not a binomial experiment anymore. So this here is already gonna break it, and it doesn't really matter for us to move forward. We just say no, this is not a binomial experiment because the trials are not independent, meaning that the probability of a success is not always the same in every single trial, right? So this kind of leads already to the fourth one, says the probability of success is always the same. So the probability of getting a defective phone has to always be the same, or the probability of getting a good phone is always have to be the same. This is already going to affect the next condition. Once one condition is broken, that's it. We don't have a binomial experiment. This is not a binomial experiment because the trials are not independent, and the probability of success is not the same, right, in each trial. All right, so you have to be really careful. You do need to make sure that you check, especially when I ask you. So if suppose that I ask you this question again later on in the semester, I do want you to go ahead and list out which ones work, and then where does it happen. So in this case, this is where it happened, right? They were not independent, and then I explained a little bit about why. All right, let's go ahead and try an example. Whenever we're actually finding those probabilities, we do have a formula. We do. I will leave this formula here for you just in case you want to do it by hand. But I prefer to teach you on a calculator or on StatCrunch because when you do things by hand, it's more prone to making mistakes. I do want to leave it for you. This is option 1, just using the binomial formula to be able to find your probabilities. But option number 2, which is preferred option, is just like how to use it, how to use your calculator or how to use StatCrunch. Okay, which I'll show you both. You can use this formula to be able to find your results. But let's go ahead and jump into example 3. It says 5% of all DVD players manufactured by a large electronics company are defective. So notice that they're already telling you what the probability of being defective is. The company knows that because of previous years, 5% of their DVDs that they make are going to be defective. It says a quality control inspector randomly selects 3 DVD players from a production line. And then it says, what is the probability that exactly one of these 3 DVD players is defective? Let's go ahead and think about, is this a binomial experiment? It has to have a fixed number of trials. Yes, right? They're going to be selecting 3 DVD players. Selecting is a trial. There is a fixed number of trials. There's 3. Every time that we do a trial, there are only 2 outcomes. So every time that we select a DVD player, in this case, it could be either good quality, right? Good condition, or it could be defective. So yes, there's 2 different outcomes for every time that we pick a DVD player. The next one is that the trials are independent. We do know that the probability of a defective DVD player is 5%, right? So every single time, the probability of being defective is 5%. So the probability of one is not going to affect the probability of the other. And then that also, again, goes with the fourth one, which is the probability of success always the same. If we choose defective to be a success in this case, then yes, the probability of success, the probability it's defective, it's always 5%. We verbally checked that it satisfies those 4 conditions for a binomial experiment. I'm going to go ahead and highlight things that are important. 5%, That's important because that's telling us what the probability of being defective is. We're told that we're going to randomly select 3 DVD players from a production line. So that's telling us the number of trials that we have. And then at the end, it's asking us what is the probability that exactly one of these 3 DVD players is defective. So we're looking for, okay, well, out of these 3, just one, right? My X here is 1. My X is the number of successes out of, this N number of trials. Okay, so let me go ahead and write all that stuff down. So we have N, which is the total number of trials, 3 DVD players, and then X is the number of successes here. We want to find the probability that one of these 3 DVD players that I get at random is defective. So X here is, again, the number of successes. We're gonna say that a success here will be defective since the question is asking us for a defective DVD player. It just depends, what the problem is that, that's gonna guide you on what is a success and what is a failure. Let me write that down. So S here would be a defective DVD player in this case, because again, the question at the end is asking us about defectiveness. So a success is a defective DVD player. So X would be the number of successes or the number of DVD players that we want to look for that are defective. And this is a 1. What is the probability of success? What's little p? What's the probability of success? The probability that it's defective, right? Because the success is defective in this case, and that's 5%. We want to make sure that we write it as a decimal though, because our calculator is not going to accept 5%. It's not going to accept the percentage. It's going to accept in decimal. So 0.05 is the same as 5%. Little p represents the probability of success. So little p is the probability of success. In this case, success is being defective, so that's 5%. If you're doing it by hand, you do need N, you do need X, which we found, N, X. You do need the probability of success, which is 0.05, and you would need the probability of failure, which is 1 minus P. And in this case, it would be 0.95. So if you were doing it by hand, you would need to find Q. But if you just use your calculator, all you need is N, P, and X. So let me just show you how to use the calculator in this case. We're looking for the probability that X is equal to 1. And the probability that my success is 1, that I have 1 defective DVD player. So let me show you how to use your calculator. Again, remember there's steps right here. We're going to hit second and then vars, and then we're going to select binomial PDF. We're going to hit enter, and then we're going to go ahead and type in what is my N, what is my P, and what is my X, and show you. I have my graph in calc. This is the same calculator as TI-83 and above. All right, so we're going to hit second. We're going to hit vars. And notice that we have normal PDF, we have normal CDF, and then at the very bottom right here, we have normal PDF. I'm going to go ahead and click that one. We're going to pick the number of trials, my probability of success, in this case, the probability of being defective. And then the last thing that we're going to do is the number of successes. So my N here is we have 3 DVDs. The probability that it's defective is 0.05 or 5%, right? We have to write it as a decimal. And then we're looking for the probability that one of them is defective. So we just hit enter and bam, it calculates it for us. Okay, so the probability that we pull 3 DVDs, that one of those DVDs is defective, is 0.135 or 13.5%. The probability that X is equal to 1, that we have 1 success, is 0.135. Using technology, the probability that exactly one of the randomly selected DVD players is defective is 13.5%. Stop there for a second to catch up. I'm going to show you how to use StatCrunch as well. Okay, so let me show you how to use StatCrunch. I'm going to go ahead and stop sharing this. And then, hello. So I have StatCrunch here. All I did was I went to my 11 mastering. I clicked StatCrunch on the tab, and then I just opened it up on the website. The steps are a little bit different here. we're gonna go to stat, and we're gonna be going to calculator. So we want to use a binomial calculator because we're doing a binomial experiment, right? We're working on a binomial problem. So we're gonna go ahead and hit binomial. My n here is 3. My probability of success is 0.05. And I want my x to be equal to 1, right? I want my probability of getting 1. The probability of success is equal to 1, and I hit compute. And notice that I get the same answer here. All right, so it's going to end up being 0.135, which is the same as the one we got in the calculator. All right, so let's go ahead and try another problem. So we have a biologist is studying a new hybrid tomato. It is known that the seeds of this hybrid tomato have a probability of 0.70 or 0.70 of germinating. The biologist plants 6 seeds. And A is asking us, does this procedure result in a binomial distribution? All right, well, let's figure out if it satisfies the 4 conditions, right? So let's go ahead and write them down. Condition 1, is there a fixed number of trials? In this case, the trial would be planting seeds. It looks like the biologist plants 6 seeds, so there is a stopping point of planting seeds. It's a fixed number of trials here. So the number of trials is 6 because we are planting 6 seeds. All right. Now, the next one is, does each trial have only 2 outcomes? A trial would be planting a seed. Every time when we plant a seed, what can happen with the seed? It could germinate or it could not germinate, right? Just die. There are only 2 outcomes. There are only 2 outcomes, germinating and not germinating. Third one is every trial is independent. Here we know that the trials, he's just planting seeds. The probability that one seed germinates is not going to affect the probability that the other one germinates, especially because they told us that the probability of germinating is 0.7, right, which is 70%. We know that the probability that it germinates is staying constant. So that's going to also guide us into the independent condition. The trials are independent. Like I said, the probability that one germinates, or again, let's just assume for the purpose of this example that the probability of one germinating is not affecting the probability of the other. And the reason why I'm saying the purpose of this example is because there are a lot of factors that go into like if things grow or not, right? In this case, we are told that the probability that a seed germinates for this hybrid tomato is 70%. Let's go ahead and talk about 4. So the last one is the probability of success always constant? And so if we're taking a success to be germinating, yeah, right? The probability that it germinates is the same every time. It's 0.70 or 0.7 or 70%. Okay, so the probability that it germinates is always the same. The probability it doesn't germinate would be 30%, right? Or 0.30, which would be 1 minus the probability of germinating. The probability of germinating is the same in every trial, which is 0.70. All right, okay, great. So it does satisfy all of the 4 conditions. So great, we can go ahead and move forward. The first question says, what is the probability that exactly 4 seeds will germinate? So out of the 6 seeds that we planted, right, so let me go ahead and draw a little picture because I like sketching. Here is my pot. I'm gonna make a generic pot, even though there's like some really cool pots out there now. So let's go ahead and put, here's my little soil, and we have 6 seeds. 1, 2, 3, 4, 5, 6. All right, what's the probability that exactly 4, 1, 2, 3, 4, that exactly 4 will germinate? Right, to give us, some yummy hybrid tomatoes. We do have our calculator, right? We have our StatCrunch as well. So let's just go ahead and write some stuff down that we're gonna need to use. So we're gonna need to know what n is, or fixed number of trials. And we know that we're planting 6 seeds. So n is 6, right? Or number of trials. We're gonna have to know what our probability of success is. And in this case, success would be germinating. And that's because our question is asking us that, right? It's asking us the probability of germination. So whatever that question is asking you, that's going to help you understand like what would it be a success in this case. P would be the probability of success or germinating in this case, of success slash germinating in this case, that is 0.70. That's given to us. And then how many successes do we want? How many seeds do we want to germinate? In this case, it's exactly 4. And so we're looking for the probability that X is equal to 4. That exactly 4 germinate. I'm gonna go and use my graph and calc. I'm gonna go to second and then vars. I'm gonna go all the way to the option down here, binomial PDF. Click on that. I'm gonna write down my number of trials, which is 6 seeds. My probability of success, which is 0.70, that's the probability of germinating. And I'm looking for the probability that exactly 4 of those seeds germinate. And I hit enter and ta-da, there it is. The probability that 4 seeds germinate out of 6 seeds is 0.324. 0.324. Let's go ahead and write this as a sentence. The probability that exactly 4 seeds would germinate out of 6 is 0.324 or 32.4%. Okie dokie. All right, so let's make things a little bit more interesting. Let's go ahead and add a little bit of different wording in there. So C is asking us, what is the probability that at least 4 seeds would germinate? So what does that word at least mean? It means that the minimum is 4, that we want 4 or more. So again, I want to make sure that you guys understand that that when you see at least, it's not less, okay? That it's that value or more. What is the probability that 4 or more seeds will germinate? Okay. And I actually did add a little table on the next page. For example, if you're asked to find at least 4, that's the same thing as 4 or more. Another way of saying that is no fewer than 4 successes, not less than 4 successes. Okay, if they tell you 4 or fewer, then you know that it's at most 4 successes. This is the same way of saying the same 4 things. No more than 4, it means 4 or fewer. At most 4, the number of successes does not exceed 4. So this little table hopefully also gives you a little guidance on, you know, if they say it this way, okay, that means it's also this, and it also means this. Right? Just because again, the English language can be a little bit hard, especially if like that's your second language. Like for me, that's my second language, so it's always nice for me to know alternative ways of saying something. So now we're looking in the probability that 4 or more germinate, and so I want to make sure that you understand the symbols as well. If we have a symbol that is pointing towards the left, this is less than. If it's pointing towards the right, we say right. We say not right. If it's pointing towards the right, we say this is greater than. If it's pointing towards the left and it has an equal symbol at the bottom, this is less than or equal to. And if it's pointing towards the right and it has an equal symbol, then it's gonna be greater than or equal to. So here we're looking for 4 or more. Using this notation, the probability that X being the number of successes and in trials, X being 4 or more, right? So X has to be greater than or equal to 4. So this is what we're looking for now. The probability that it's 4 or more, well, we know that we planted 6 seeds. 4 or more would be the probability that we get 4 seeds that germinate, or 5 seeds germinate, or 6 seeds germinate out of 6. And that keyword or, remember in probability, is addition. So we're gonna go ahead and add all of those probabilities together. So this is the same thing as the probability that X is equal to 4, or the probability that X is equal to 5, or the probability that X is equal to 6. So the probability that X is equal to 4 plus the probability that X is equal to 5 plus the probability that X is equal to 6. So we actually already found this one. We found that one in the previous part, remember? The probability that we have exactly 4 seeds germinating, We already found that 0.324. And now we're going to use the same procedure to find the probability of that x is equal to 5 and the probability that x is equal to 6. So let me show you how to do the calculator one. So we're going to go ahead and hit second vars, binomial PDF. We have 6 trials. My probability of germinating is still the same. And now I want 5 successes. I hit enter. I'm going to go ahead and do that again. 6, we have 6 trials. The probability of success is 0.70. And I want 6 successes out of 6. So we hit enter. And what we're doing is we're adding these probabilities together. Probably that we have 4, plus the probability that 5 germinate, plus the probability that 6 germinate, because that would be 4 or more. So we have 0.324 plus 0.303 plus 0.118. We're going to go ahead and add up all of those probabilities, and that's going to give us a probability that at least 4 seeds will germinate. Go ahead and add those up, and hopefully you get the same thing that I get, 0.745. And if you don't, please let me know at some point and make a note and talk to me in office hours or in class. All right, so let's go ahead and write that down. The probability that at least 4 seeds will germinate is 0.745 or 74.5%. Let me show you how you can also use StatCrunch. And StatCrunch is actually, it makes things a lot faster as well. So let me just show you how we can actually find this a little bit faster. So we have 6 trials. The probability of germinating is 70%, which is 0.70. And we're looking for greater than or equal to 4. And we hit compute, bam, it gives us the same thing. Do you see? The probability of getting 0 is this much. I don't know, I can't really tell what that is. And then 1, the probability of getting 2 is right here. The probability that x is equal to 3 is this value here. Probability that's equal to 4 here, 5 here, 6 here. And so it's adding up the last 3 here, the probabilities of the last 3. And that's what the outcome is. And it's pretty close to ours. I think ours rounded is 0.7445. It's really close. It's off by 0.001. So yeah, so the binomial calculator on StatCrunch is really cool. Okay, you can already find all of them. You don't have to actually add one individual one at a time. You can just change the symbol. You know, if you want less than 4 successes, there you go. That's what it gives you. If you want greater than 4 successes, strictly greater, right? 5 and 6, then it'll give you that. If you want exactly equal to 4, then it gives you the amount that we found. Okay. So again, the reason why we're off by a little bit is because I rounded at every single probability. Okay, so this one is actually more accurate than the one that I found. But again, on your practice assignments, it's going to tell you what to round it to. So just round until the very end. On StatCrunch, this result, if we round to 3 decimals, it was 0.744. The reason why ours is a little bit off is because I rounded in the previous step. So you actually want to round until the very end. So I should leave more decimal places in these values so that at the end, my value is more accurate. It's just that whenever you round at every step, the answer is going to be a little bit different at the very end because of rounding, right? It's best to just use exact values. But it's okay. It's like this, if you put this, on your practice assignment, it would still accept it, okay? Because it's only off by 0.001. All right, we're almost there, everybody. Just hang in there. We're almost done. So again, I told you guys this is a common English expressions for the same thing. So again, if if you're having any trouble, go ahead and look at that table. And the last thing that I want to talk about is how to find the mean, the variance, and the standard deviation for a binomial probability distribution. And in order for us to find the mean, all we have to do is multiply the number of trials times the probability of success. If we want to find the variance, we're going to have to do the number of trials times the probability of success times the probability of failure. And to find the standard deviation, all we do is take the square root of this one, and that will give us the standard deviation. So I wanted to make sure that you guys were comfortable using these formulas. So I ended up adding one last example here. Okay. It says, assume that different groups of couples use XOR method of gender selection, and each couple gives birth to one baby. So we have different couples that are using this method, okay, and each couple just gives birth to one baby. Okay, so there's no twins here. The XOR method is designed to increase the likelihood that a baby will be a girl, but assume that the method has no effect, so the probability of a girl is 0.5. And assume that the group consists of 36 couples. So it's asking us find the mean and the standard deviation for the number of girls in groups of 36 births. All right, well, let's see. Mu is equal to n times p. We have the number of trials. We have 36, right? We have 36 births, and the probability of getting a girl here is 0.5. The average here, the mean is just half of 36, which is 18, right? So 18.0 girls. So the mean number of girls in a group of 36 birds is just 18, right? So because the probability of getting a girl is half, then half of these birds are going to be girls. All right. Now the standard deviation is equal to the square root of n times p times q. All right, well, the square root of n is 36. The probability of success is 0.5. The probability of getting a boy is 0.5, because again, remember that q is 1 minus p, and if my p is 0.5, then my q is 0.5. If I multiply all this together, I end up getting 3.0 girls. So my standard deviation is 3 girls. Use the range rule of thumb to find the value separating results that are significantly low and significantly high. Okay, well, we know that a value would be significant if it's 2 standard deviations away from the mean. I'm going to go ahead and draw my little table again because I like doing my little number line. Here's my mean. Again, if I am 2 standard deviations above my mean, then I would be significantly high. And if I am 2 standard deviations below my mean, then I would be considered to be significantly low. So I'm looking for these values here. I'm looking for what are those values separating the results that are significantly low and significantly high. So we're going to have to find mu plus 2 sigma and mu minus 2 sigma. So we have mu plus 2 sigma. So this is going to be 18 plus 2 times 3, because we know that sigma or standard deviation is 3. So then we have 18 plus 6, which gives us 24.0 girls. Mu minus 2 sigma is 18 minus 2 times 3, which is equal to 18 minus 6, which is 12 girls, 12.0 girls. If we're not using any method to help us have higher likelihood of having a girl, then having 24 girls or anything above that in 36 births, that would be a significantly high number of girls in 36 births. And if we have 12 or less than that in 36 births, that would be considered unusually low, like, unusually a low amount of girls. So this value here is 24. This value here is 12. Okay, so if we have 24 girls or more, then that would be a significantly high number of birds having girls. If it's 12 or below, that's a significantly low number of girls in 36 births. Okay. So now it's part C says, is the result of 26 girls a result that is significantly high? What does it suggest about the effectiveness of the XOR method? So let's suppose that for the XOR method, that they end up having 26 girls out of 36 births. Right? Let's say that they take this, they take this medication to increase the likelihood of having a baby girl, and that using this method, there's 26 out of 36 births. Because 26 is more than 24, right? It's in this area here, then yeah, 26 girls would be considered significantly high. And that would mean that that XOR method is effective. Does that make sense? I hope it does. So let me write that down. So 26 girls in 36 births would be considered significantly high. If these were the results from using, again, if this is the results from using XOR method, then it would suggest it is an effective method. Then this suggests that this method does increase the likelihood of having a baby girl.
All right, everybody. So thank you so much for joining me for this lesson on binomial probability distribution. I did show you how to use the calculator and how to use StatCrunch as well for these calculations. If you have any more questions, please look at the module. The module actually has videos on how to use StatCrunch for some of your practice assignments, and it also has videos on how to use a calculator for the practice assignments as well. So there's videos for both. Take advantage of those resources. Just look at the module for this week and you'll be able to find those. All right, everybody. See you next time.